Hey, everybody. Hope you're having a good one. Today, we are going to be going over the pentose phosphate pathway. Now, we'll talk about a couple of different metabolic pathways. We've already talked about glycolysis, but I want to get into this one because it's a little bit simpler, I think. And in terms of the volume of information that you need to recall, this is a little bit less than glycolysis. Now, with that in mind, if you remember, whenever we talked about glycolysis and we talked about the enzymes of glycolysis, there was a heavy emphasis on the irreversible steps. And if you remember, the first step in glycolysis is the conversion from glucose to glucose 6 phosphate. That's a phosphorylation done by hexokinase or in the liver, done by glucokinase. Now, with that, that was the first irreversible step. But one thing that's really important is that although it was irreversible, it was not the first committed step. And I bring that up because this pathway, the pentose phosphate pathway, is going to be worthwhile whenever it comes to thinking about an irreversible and a committed step. Okay, so the pentose phosphate pathway is this pathway that we're going to be going through. We have a couple of simple and short learning objectives. We want to look at the two phases of the pentose phosphate pathway. They are the oxidative and non-oxidative phase. We want to look at and understand the importance of NADPH in cellular metabolism. We want to identify the key enzymes of the oxidative phase. That's one of your key enzymes. And then last but not least, we want to explain the pentose phosphate pathway and how it interacts with glycolysis. So, the first learning objective that we're going to get after is looking at this pathway kind of globally and then looking at the two phases. Now, one thing that I think is really important to recognize about this pathway is where do you start? Okay, so we start in this upper left-hand corner right here with none other than glucose 6 phosphate. Well, where do you think that came from? If you think about the learning objectives, we're going to talk about this pathway and how it interacts with glycolysis. Well, what's our first product in glycolysis? Or what's the first metabolite that's produced in glycolysis? Well, that's none other than glucose 6 phosphate. So I think that this is a good point to remember. Well, I'm going to say HK, hexokinase, is irreversible, but not committed to glycolysis, glycolysis. Okay, so it's the first committed step, and but it's not committed to glycolysis. And evidence of that is that glucose 6 phosphate is generated by hexokinase. And this pathway that I'm showing you guys right here is a different pathway. It is not glycolysis. Okay, so that's the first thing that I want to mention. Then what I want you to mention is, or then what I want you to understand is, okay, we've got, looking at our arrows, we've got an arrow here, 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 and we've got something that splits off. Ooh. And then we've got this. Oh, this is a reversible reaction. And oh man, it's complicated because it's reversible and then it kind of splits off and goes in different directions. There's like a fork in the road. And if you follow some of these arrows, like if we follow the arrow labeled 4, that's going to give us this intermediate. If we follow that intermediate, we go to transketolase, the one that's labeled 6, that's going to give us this. Oh, but then there's this other molecule, and then that other molecule, oh, we're going to transaldolase, and that's reversible. And if you follow all of those metabolites and all of those reactants, well, it's going to make a cycle. And that's one of the elements or one aspect that I think makes the pentose phosphate pathway particularly challenging. Now, what I want you to know right now is that we can break this pathway down into two major phases. The first phase is depicted right here. This is known as our oxidative phase. And there's a couple of really important details that I want to highlight about this oxidative phase. And I think the way to highlight that is by looking at all of the arrows that don't go from our carbon-based structure here to this one, and to this one, to this one, but instead to look at kind of the byproducts. And I'm going to highlight those or circle those right here. Then we've got this. We've also got that proton there. Then this and this. Okay. So what I think is important to kind of appreciate and understand about the oxidative phase is that we are going to generate in this oxidative phase two NADPH. Okay, so we're going to get two NADPH produced from this. The other major product that we're going to generate from this is going to be, well, none other than CO2. Okay, now the next part that is going to take what we just wrote down here and add a wrinkle to it is, well, let's think about this for a moment. We have glucose 6-phosphate, probably coming from glycolysis, and that is acted on by glucose 6-phosphate dehydrogenase. Okay, that name dehydrogenase is a good thing to remember whenever you're thinking about an enzyme that's making NADH or NADPH. Okay, then we make this 6-phosphoglucanolactone. That's going to be acted on by 6-phosphoglucanolactonase, which is going to produce 6-phosphogluconate, which is going to be acted upon by 6-phosphogluconate dehydrogenase, and that's going to produce ribulose 5-phosphate, or RU5P. So you could think about the oxidative phase and say the starting point is, well, it's glucose 6-phosphate. Our end point is ribulose 5-phosphate. Not to be mistaken with ribose. This is ribulose. Now, that's a good place to start. You know, if you're kind of building up your knowledge and understanding of the pentose phosphate pathway, I would think at the very base, I'm saying the oxidative phase. My next level is to say, okay, well, I start with glucose 6-phosphate, I generate some NADPH, and then I also generate ribulose 5-phosphate. Okay. Now, the next thing that I want to draw your attention to, I'm going to clear all my drawings on this first phase, or all my writings, and I'm going to put a box around this right here. Now, in the video that, or the slide that I'm looking at, I can see this. If you get the PowerPoint file or the PDF and zoom into it, I think that you'd see this as well. I know whenever I was first learning about the pentose phosphate pathway, I remember looking at the contents of that box and thinking to myself, like, oh, cool arrow. It's almost like I was interpreting it as like stylistically. Someone wanted to, you know, go back to the 1970s and draw a really cool arrow. Well, if you look closely at that arrow, you're going to see it looks a little bit like this. 1, 2, 3. It's going to look like that. And I bring this up because there's significance to that. Those 3 lines behind that arrow really indicate that everything here, this glucose 6-phosphate, this NADPH, all of the intermediates and all the products, well, we need to triple that. So what that means is that I'm going to take this oxidative phase and I'm going to say the oxidative phase, I'll draw an arrow, starts with 3 G6P and ends with 3 Ru5P. And when you're looking at this, you might be thinking, what, why do we have to? And my answer to that question is, well, or actually, let me rephrase the question and say, can one glucose 6 phosphate be acted upon by glucose 6 phosphate dehydrogenase, go through all of this to produce one ribulose 5 phosphate? Yes, the answer to that question is absolutely. So the oxidative phase, really, you only need one glucose 6 phosphate. And from that one glucose 6 phosphate, you're going to make one ribulose 5 phosphate. But that's the oxidative phase. The oxidative phase feeds into the non-oxidative phase. So the way that I always think about the pentose phosphate pathway is I think, okay, well, the first phase feeds into the second phase. And so all of the action that's taking place in the first phase is almost preparation for the second phase. So that's why I go ahead and I take my thoughts on the oxidative phase and I say that it starts with 3 glucose 6 phosphate and it produces 3 ribulose 5 phosphate. And in the process, it's going to make 6 NADPH and 3 CO2. So those are the parts that I'm going to kind of that's the way that I'm going to kind of modify and contort my knowledge so that I can kind of balance my understanding of the oxidative phase with the non-oxidative phase. So if you're thinking, okay, what do I need to know for the oxidative phase? You need to know that it starts with glucose 6 phosphate and it concludes with ribulose 5 phosphate. Along the way, you make NADPH. Now, if you're going to fine tune that knowledge and say, okay, well, what do I need to know with like a fine tuned or a nuanced understanding? Well, I need to know that I'm starting the oxidative phase with 3 glucose 6 phosphates, and I'm going to conclude it with 3 ribulose 5 phosphates. I'm also going to produce 6 NADPH and 3 CO2s. So with that, one of the things that I always like to do is I like to think in terms of pure numbers of carbons. If I'm making 6 NADPH and 3 CO2, well, I'm starting with, and this is, I'm going to go slowly on this just so everyone can follow it. Glucose 6 phosphate has 6 carbons, and I have 3 of them. So I'm starting with a total of 18 carbons. When I reach the concluding point where my ribulose 5 phosphate is, well, one of my products has been CO2. But remember, this is taking place 3 times over. So I'm going to make 3 CO2. I'm going to be left with 3 ribulose 5 phosphates, which ribulose 5 phosphate is a 5 carbon molecule. So I'm going to say 3 times 5 carbons, which is 18, not 18, 15 carbons. So this is important because what we're going to see in the non-oxidative phase is we're going to be kind of scrambling and shuffling these carbons around. So we've got 15 carbons that are leaving the oxidative phase. Okay, so what are the important priority pieces of information so far? What's your input? What's your output? And your ratio. Those are the big things about the oxidative phase. Now, we start our non-oxidative phase. And I'm just going to go ahead and write it here, Ru5P, and I'm going to put in parentheses 3, which then I'm going to go ahead and say 15 carbons. I like to do that because I think that it makes a little bit more sense. We've got 3 of these ribulose 5 phosphate molecules. And you know what? If you look super closely at these arrows right here and this arrow right here, there's 1 arrow right here, there's 2 arrows right here. Okay, so what one of my ribulose 5-phosphate molecules is going to kind of undergo, it's going to be isomerized to make ribose 5-phosphate. This is a 5-carbon molecule. What about our other two? Well, our other two ribulose 5-phosphate molecules, I'm going to swing this arrow by the 2 to indicate that the remaining two of those molecules are going here. They're going to be acted upon by an epimerase, and we're going to make xylulose 5-phosphate, which that is two 5-carbon molecules. Okay, so we've got 10 carbons. So I'm going to say 5 carbons here, 10 carbons among the two xylulose 5-phosphate molecules. I'm going to erase that just so that it doesn't produce any kind of confusion. Okay. So basically, I'm going to be walking through some of these steps, but what I want you to know for your priority knowledge for the second phase, our non-ox phase, basically what you're doing is you're isomerizing and you are making glycolysis intermediates. Okay. And intermediates meaning molecules that can be plugged into glycolysis. Okay. So back to where we were. We've got xylulose 5-phosphate, ribose 5-phosphate. We've got two xylulose 5-phosphates and one ribose 5-phosphate. And there's this enzyme here, transketolase. What it's going to do is it's going to take the 5 carbons that make up ribose 5-phosphate, and then it's going to take these 2 carbons right here from the top of a xylulose 5-phosphate molecule, and it's going to combine those two to make, well, let's see, if we add a 5-carbon molecule to a 2-carbon molecule, a 7-carbon molecule. Did you see that magic? And that 7-carbon molecule is cetoheptulose 7-phosphate. But what happens to the other 3 carbons of that xylulose 5-phosphate molecule? Well, these become that right there, glyceraldehyde 3-phosphate. Okay, now stop the press real quick. We've taken 2 5-carbon molecules and we made a 7-carbon molecule, and we've left behind a 3-carbon molecule. That 3-carbon molecule, glyceraldehyde 3-phosphate, have we seen that before? We have. Where did we see glyceraldehyde 3-phosphate? We saw glyceraldehyde 3-phosphate in the production of, or sorry, that is one of the products of the aldolase mechanism of glycolysis. So where we make our glyceraldehyde 3-phosphate and dihydroxyacetone phosphate, those two compounds generated by aldolase are glycolysis intermediates. Okay, so I would say that that is the biggest point where I kind of want you to be able to like take a pause and say, okay, I see what's happening. Now, is there more to this reaction? Is there more to this pathway? Absolutely. One of the things that I want you to see is that that's a reversible reaction. This is a reversible reaction. Not only is it reversible, but this reversible reaction goes all the way up here. This reversible reaction goes here, and it goes here. Like these reversible reactions kind of go all over the place. What did I say were your important priorities for the non-oxidative phase? I want you to know that we've got lots of isomerizations, kind of scrambling carbons around, and in the process, making glycolysis intermediates. This is the non-oxidative phase. I also want you to know that we're starting with Ru5P because that's our endpoint from the oxidative phase. I apologize for yawning. So those are our priorities for the non-oxidative phase of the pentose phosphate pathway. Okay, now the learning objective or next learning objective is I want you to understand the importance of NADPH in cellular metabolism. Now, what we have is two major molecules, NADH and NADPH. NADH, what is the role of that? Well, this is a compound in a molecule, NADH, that's going to be used for the, or whenever NADH is made, we're going to use that in something known as the electron transport chain so that we can generate ATP. So think about NADH as being for energy production. Meanwhile, NADPH. What's the role of NADPH? Well, that is going to be used in biosynthesis. Now, these two molecules, they're going to exist in two major different places and kind of states. For instance, there's the NAD plus, the oxidized form of it, of this molecule, and NADH. Our ratio is going to tremendously favor the presence of NAD plus because whenever we have NADH, we want to go ahead and extract or basically produce ATP from that. So what NAD plus is going to do is it's going to remove a pair of electrons. Um, as we saw in glycolysis, it's removing electrons from a compound. So that's why NAD plus gets reduced. Okay, NADPH, by contrast. Well, that's the form that we're going to mostly see this compound in. And what this is going to do is it's going to add electrons during biosynthesis. So this is primarily for the production of compounds. For example, fatty acids. That's one of the ways that NADPH is going to be used. And so we'll save that for a little bit later. Okay. Now that's what I want you to know about NADPH versus NADH. What are their roles and um, what makes them different from one another? Spoiler, what makes them different is phosphorus. But NADH is used primarily in energy production, whereas NADPH is used primarily for biosynthesis. So one way you could think about them as different is NADPH is involved in fat production, whereas NADH is, well, we're going to make a bunch of NADH when we're breaking down a fat. Okay, then what I wanted you to understand was I want you to know the key enzymes of the oxidative phase. Now, the key enzymes of the oxidative phase are the two steps, number 1 and number 3, that are responsible for producing NADPH. So those steps are glucose 6-phosphate dehydrogenase. This is also known as G6PDH. Our other step is 6-phosphogluconate dehydrogenase. 6-PGDH. 6-phosphogluconate dehydrogenase. The significance and the importance of these steps is that they both produce NADPH. So steps 1 and 3. Now, what's happening here? Well, we are basically taking electrons. If you look at this and say, okay, where? Well, what this enzyme is going to do is it's going to see our anomeric carbon right here. And it's going to convert that from an OH and a hydrogen, and it's going to make it's going to make a lactone, but it's also just going to make a carbonyl carbon there. So that's kind of our target. We're going to pluck off this hydrogen and a proton. Then our next enzyme, this lactonase, what it's going to do is it's going to open up this ring. We've got 6-phosphogluconate, where now carbon number 1 is a carboxyl group. So we're making this an acid. Then what we can do with that is we can go ahead and remove we can remove this hydrogen right here, remove our CO2, and convert this right here from a hydroxyl to a carbonyl carbon. And that is done by 6-phosphogluconate dehydrogenase. All right. Now, those were the important parts about the oxidative phase, the non-oxidative phase, NADPH, and NADH. If you're looking at this and thinking to yourselves, well, there's not a lot of information. I would agree with that. Is there considerably less information than what is in glycolysis? 100%. No doubt in my mind. Does that mean that this is a less important pathway? No, it doesn't. What it means instead is that this pathway is kind of an offshoot of glycolysis. It serves a different purpose. There's a different role behind us having this pathway. What do you need to know about this? Well, I kind of highlighted those things in the previous slides, but this is a pathway that you're going to go into a bit more detail when you take metabolism. But I wanted to show you a pathway that isn't just straight up and down. Instead, we've got kind of two major phases, and they are an oxidative and a non-oxidative phase. Now, what I want you to look at and what we're going to review here is the crosstalk or the interconnectivity of glycolysis and the pentose phosphate pathway. So this pathway really simplifies things quite a bit. If you look on the far left-hand side of your slide, what you'll see right here is you will see glycolysis. That's all there is to glycolysis. Glucose goes to glucose 6-phosphate, which goes to fructose 6-phosphate, which goes to glyceraldehyde 3-phosphate, which ends up pyruvate. Is there some ATP and NADH developed and produced along the way? Totally. Okay, fair enough. Now, the first thing that's worth noting about this is let's look at that pathway, but look at where the pentose phosphate pathway kind of takes off. Well, the pentose phosphate pathway takes off at glucose 6-phosphate. Key detail to remember, 3 glucose 6-phosphates. Okay, what we're going to do is we're going to make some CO2. This, again, this is just a very basic summary. This is not quantifying the number of ATP or NADH or NADPH or anything like that. This is just saying, hey, some of this is generated. So don't get distracted by that. This glucose 6-phosphate will generate that and will end at ribulose 5-phosphate. That ribulose 5-phosphate right there is going to be scrambled around and be shuffled around. One of the things that it's going to use, or that it's going to be used for, is to produce ribose 5-phosphate, which can be used for the synthesis of nucleotides, so DNA. Okay, cool. So that's one thing that it's going to play in with. What it can also be used for is that xylulose 5-phosphate, which ultimately we can feed this into fructose 6-phosphate, which we didn't explore that, but also more directly, we can feed this into glyceraldehyde 3-phosphate, or GAP. Now, as soon as we get that, that GAP can be used for ATP and NADH production as well as pyruvate. Now, how should you look at the connection between the pentose phosphate pathway and glycolysis? Is there one pathway that's more important? Sure. Yeah, I think that's fair to say. How do you determine or know which one's more important? Fair question. I think that the way that I kind of visualize it is glycolysis is a pathway where it's almost like, here's a little analogy. Glycolysis is the pathway that makes sure that you eat dinner tonight. So that's the pathway where you're using your money to buy bread. Okay. Hope I don't go too distant on my analogies here. The pentose phosphate pathway is saying, hey, we've got extra money. Let's put some of it away. Let's save some of that energy. So let's take that glucose 6-phosphate and not break it down so we can generate ATP, but instead, let's plug that into something like some nucleotides. Because you know what? The cells that we're in, we're going to undergo some replication, so we want to be ready for that. And just general production of nucleotides as well as fatty acids. We can build up these fatty acids so they can store a bunch of energy. And then when we need to, we can break them down. Okay. So my answer to the question of which one's a higher priority or which one's more important, glycolysis, because you need that to exist. Whereas the pentose phosphate pathway, it's kind of a detour. Do you come back to the main road? Yeah, absolutely. Which is another kind of illustration as to why it's framed and presented as, well, glycolysis is priority and pentose phosphate is secondary. But that's just because the literature and the results on experiments done with these enzymes supports that idea. So what I want you to know about this is I want you to know where glucose 6-phosphate is with respect to the pentose phosphate pathway. I also want you to know about how the pentose phosphate pathway can hook back up with glycolysis. Now, like I said, glyceraldehyde 3-phosphate was the primary place where I talked about us rejoining glycolysis, but this other one, fructose 6-phosphate. Let's go back and look at our secondary process or our non-oxidative phase. Well, fructose 6-phosphate is an intermediate in this non-oxidative phase. So where we go back into glycolysis is in this non-oxidative phase of the pentose phosphate pathway. Now, the way that I always kind of think about this pathway is I always kind of think about we've got, I hope this makes sense. If it doesn't, then please either say I didn't understand that, I needed a different explanation, or say, yeah, that worked. The way that I always kind of think about this is I'm starting with ribulose 5-phosphate. I've got three copies of that molecule. When this is taking place in the cell, do I only have 3 ribulose 5-phosphate molecules? In a cell, do you only have like 3 of basically anything? No, you've got tons of them. So what I always think is that we've got these circles that I drew are basically buckets where we've got tons of these intermediates, tons of these metabolites. And what happens is we have these molecules that are input, and basically they fill up these different buckets. And whenever those buckets are full, well, they'll go on. And sometimes this glyceraldehyde 3-phosphate bucket might be super overloaded, in which case, well, they have a fate for those molecules, and they can be glycolysis. Fructose 6-phosphate, there's a bucket there, and when that thing begins to overflow or overflows altogether, well, then that can be plugged into the glycolysis. Okay, so there's a bit to understand about this, but I think that it's a complicated but somewhat simplistic pathway. What I want you to do is think big picture and then narrow in. I have asked you to focus a little bit more on the oxidative phase or the oxidative phase than the non-oxidative phase. So do that. Okay, well, I hope you have a good one, and I will see you later. And